Good morning, everybody. So I have some notes to record for you. This is actually going to be part one of our nuclear chemistry notes. You guys will be taking these notes asynchronously, and then we will be going over some of the concepts and then doing some problems in class, okay? So here we go. So in terms of nuclear chemistry, what do you need to know? First of all, let's review some of the things you should already know. So we know that the number of the atomic number is going to equal the number of protons, right? We also know that the number of neutrons is going to equal the mass number minus the atomic number. We should also know that isotopes are going to have different numbers of neutrons. And then finally, if you guys remember, there are two different types of isotopic notation. We have the hyphen notation, which is noted down here at the bottom, and it says carbon with the hyphen, and then the mass number after it, which is 12. And then if you look at the other notation that you guys learned about, right? You have the symbol for the element, and then it represents basically the same thing, but it gives you an extra piece of information that the hyphen notation doesn't give you. So you have the number, which is the superscript. So the superscript is going to indicate the mass number, and the subscript is going to indicate the atomic number or the number of protons. Okay, so over here is just an example of isotopes of hydrogen, right? So we have protium, which its mass number is 1, and then the atomic number is 1. Then we have deuterium, which is technically classified as what we call quote-unquote heavy water, okay? And that has a mass number of 2. And then we have the same atomic number of 1, which is why it is considered hydrogen. Okay, so remember, the atomic number is going to give the character of, or the element that we're studying. And then we have tritium, which is actually a radioactive isotope of hydrogen. But if you look, the mass number is slightly different, right? It has 3 here. That means that it has 2 extra neutrons than the original, but it still has the same atomic number. Okay, so let's talk about this nucleus, right? You guys watched a video on Friday that should have just given you some more ideas or helped you review what you might already know or should already know about the nucleus, right? So we know that the nucleus contains protons and neutrons, right? Up until then, you didn't know them as having a collective term. So the nucleus, when it contains protons and neutrons, when they're together, they're known as nucleons. All right, so that's something that you guys can remember. Don't get confused when I refer to the protons and neutrons that are together as nucleons. It's obviously going to be positively charged, right? Because the protons are positive, neutrons don't have a charge. And then we need to talk about what's going to hold this nucleus together. So the nucleus gets held together by this fundamental force called the strong force. Basically, it causes protons and neutrons to be attracted to one another. It only works over very short distances, which you guys will learn more about when we start talking about some of the periodic trends and as the atomic radii of the elements get bigger and atoms get bigger and bigger and bigger. Obviously, it's going to hold on a little bit more tightly to some of its electrons as opposed to other electrons because of the distance. Okay? So, when the strong forces can keep the nucleus together, the nucleus is considered stable. And obviously, what we're going to be talking about in nuclear chemistry is kind of when the opposite happens, right? When the force is not strong enough to keep the nucleus together. Hence, we get nucleus or atoms that are unstable, and that leads us into the whole radioactive and nuclear chemistry and radioactive decay, which is basically what this is all about. Okay, so what happens when that strong force just isn't big enough? Well, guess what? The nucleus just falls apart. Okay? It does it in a very systematic way, and that's what you guys are going to be going through the lessons about and doing some extra problems about. But if we're talking about like a technical term, we say the nucleus has decayed. When this happens, just like most of the processes that we're going to study in chemistry, both matter and energy are going to be released. Nuclei that fall apart they're considered unstable, or another term for it, radioactive. Radiation is going to be released when that nucleus decays or falls apart. And then I guess we should talk about how the discovery of radioactivity came upon, or was discovered. Let me be clear. Okay, so what I want you to realize is that there are two different types of nuclei, right? We have the stable nuclei that stay together. The force is strong enough to keep it together. Then we have the flip side, which is going to be unstable, which is when that strong force just isn't strong enough to hold it together. And when that happens, the nucleus is going to decay. Matter is going to be released. Energy is going to be released. And the radiation that's released is going to make these nuclei radioactive. Okay, so how was radioactivity discovered? It was first discovered by a French scientist in 1896. He discovered it from a uranium compound. Radioactivity, the term, was actually coined by Marie Curie. So she ended up discovering two new elements of radium and polonium. So unstable atoms that fall apart and they release radiation, just to refresh, they are basically mean that they are radioactive. Okay, so radioactive studies have been going on for a while, as you can see from Henri in 1896. But Marie Curie was really instrumental in basically discovering new elements and discovering some new things about radioactivity. Okay, so now let's make a comparison. Stable versus unstable nuclei. So now you know the concept. We have stable atoms, we have unstable atoms, right? And now we're going to need to know how to figure out which ones are stable and which ones are unstable. That's the very first thing that you guys are going to have to know. So since nuclei can be stable or unstable, stable nuclei mean exactly what they're supposed to, right? They do not spontaneously change. When we talk about unstable nuclei, that means that they spontaneously change and they actually turn into nuclei of different elements. And that happens because the number of protons ends up changing. So if you remember, the character of our atom is determined by our protons. So if the proton number changes, then we are a completely different element. So unstable nuclei are just naturally built wrong and they end up falling apart. And the process when one element becomes another is called transmutation. And transmutation basically occurs when the number of protons in the nucleus ends up changing. Okay? So now let's talk about how we're going to predict all of this. Which nuclei are unstable? All atoms bigger than element 83, which is bismuth, they are considered unstable. They are radioactive. There are some smaller atoms that are also radioactive. It's going to depend on the ratio of neutrons to protons. And we're going to show you how to calculate that. Okay, so let's back it up. I want to make sure that you guys are catching everything, right? So any atoms that are bigger than element 83, bismuth, are considered unstable. They are radioactive. There are some smaller atoms that are also radioactive, but that's going to depend on the ratio of neutrons to protons, okay? So the first set of calculations that you guys are going to be doing is basically trying to figure out from the neutron and proton ratio if they are unstable. So radioactivity, aka the breaking down of the nucleus, is going to depend on this ratio. So to create a ratio, you're going to take the number of neutrons and then you're going to put it over the number of protons, and then we're going to figure out what that number is. Now, you're probably asking me, well, what am I comparing it to? How am I supposed to know that it is unstable or stable? So, here we go. Which atoms are going to be stable? A very small atom with an atomic number that is less than 20 is going to be stable if the neutron-proton ratio is very close to 1 to 1. Okay? So if you take the number of neutrons, put it over the number of protons, if you basically get a ratio that's real close to 1 to 1, then we can consider that atom stable. A large atom that has an atomic number of 20 or more is considered stable if that same neutron-proton ratio is close to 1.5 to 1. Okay, so less than 20, we're looking for a 1 to 1. More than the atomic number of 20, it's going to be a 1.5 to 1 ratio. So let's do some examples. Predict the stability of the following. Okay, so we have carbon 12. So if you think about carbon 12, you know the 12 is going to be the mass number. If it's carbon, that means that it's going to have an atomic number of 6, right? So if we look at the number of neutrons, we are going to have 6 protons and 6 neutrons. Okay, so if we have 6 protons and 6 neutrons, then it's going to be considered stable, right? 6 over 6, 1 to 1, considered stable. All right, for hydrogen, mercury, and uranium, I want you guys to pause the video and see if you can figure them out before I give you the answers. Okay, so for hydrogen 3, what that's going to mean is if it's hydrogen, we have 1 proton. That means we have 2 neutrons. Okay, so if we put the number of neutrons over the number of protons, we have a 2-to-1 ratio, not a 1-to-1 ratio. That makes it unstable. Okay, mercury 200, if you were to look at the periodic table, mercury is going to have 80 protons and 120 neutrons, right? Remember, 200 is going to be the mass number. We're subtracting it from 80 and we're getting the 120 neutrons, okay? So if we take the 120 neutrons and divide them by the 80 protons, we end up with a 1.5 to 1. So remember, the atomic number is going to be greater than 20. If it's greater than 20, for it to be considered stable, it has to be close to 1.5 to 1. And mercury 200 is 1.5 to 1, which is considered stable. Same thing for uranium 235. What I'm looking for is a 1.5 to 1 ratio. If you look in your periodic table, you should know that for an element to be uranium, it has to have 92 protons. So if you take the 238, which is the mass number, subtract it from the 92 protons, you get 146 neutrons. So now we're going to set up our ratio. Number of neutrons over the number of protons, 146 over 92. We end up with 1.6 to 1. That's considered unstable. Okay, so please keep that in mind because you're going to have to try and figure out this whole band of stability. And I'm going to ask you to predict which atoms are stable and not stable. Or unstable, let me be clear. Okay, so the last bit of information, I just want to generally talk about the difference between fission and fusion. So for nuclear fission, the definition is going to be the splitting of a large atom into smaller ones. It does not normally occur in nature. Basically, there are man-generated and they're used in nuclear power plants. And it requires very little energy. And it releases a lot of energy. Okay, so it's very favorable. We're splitting a large atom into a smaller one, even though the process is going to be tedious and requires equipment, it is in general going to require less energy and is going to release a ton of energy. When we talk about nuclear fusion, we are fusing the lighter atoms into a larger one. It occurs in stars, okay? So it happens in the sun all the time, which hopefully you guys remember from Earth science is just a big star. This, unfortunately, is going to require a lot of energy, but it releases 3 to 4 times more energy than fission reactions, okay? So what I want you to get out of this slide, we have nuclear fission is the splitting of a large atom into smaller ones. Nuclear fusion is the fusing of lighter atoms into larger ones. Nuclear fission does not happen naturally. Nuclear fusion happens naturally, happens in stars, things like that. The other one is nuclear fission requires little energy, while nuclear fusion requires a lot of energy. Nuclear fission releases a lot of energy, but nuclear fusion will release 3 to 4 times more energy than any fission reaction. Okay? So that is the end of your introduction to nuclear chemistry, and this is part 1. I'll be filming part 2. Part 2 is going to deal more with the actual types of radioactive decay, and then we're going to go through some problems that you guys might see. Okay? So I hope this was helpful. If you need something else, you know how to get in contact with me. Bye!